anyone missed the class or needs a quick refresher overview of what I taught today, sit back, relax, and enjoy, or suffer. Choose which one you want to do. So, what we have here is we talked about the basic introduction to electric charge. And so there's 4 things that you kind of need to know about electric charge, or the basics about it. First of all, there's 2 types of electric charge. There's positive and negative. We can debate and argue whether or not neutral is a 3rd type of charge. Personally, I'm going to go with the fact that it's a charge that doesn't exist. So therefore, it is not a charge. The second thing is charge comes in quantized units. This means that when you look at an atom, for example, and there's protons inside and there's electrons on the outside, the proton charge is positive 1.6 by 10 to the minus 19 coulomb. An electron is negative 1.6 by 10 to the minus 19 coulomb. You cannot have charge that exists in between those values, as in like in decimal places. It's either 2 proton charges, 2 electron charges, 3 electron charges, 4 electron charges. It cannot have values in between. The third thing about it to remember is that like charges repel and opposite charges attract. That's the third point. And the fourth point is that charge is conserved, supposedly in the whole universe. The idea behind it is let's say we grab a box and we put a bunch of ions, electrons, protons, a couple of compounds, and the total net charge, when you add up all the electrons and all the protons, the total net charge is 1 electron charge. And then you close the box and you shake it up, ooh, 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 do a bit of a Swiftie dance, and lots of stuff happen. New compounds are created, new stuff is being moved around, new ions are created. The total charge still remains the same. No matter what happened inside that box, the charge remains the same. And this is what we mean by charge is conserved. And finally, we talk about Coulomb's law, and I tell the joke where Coulomb basically copied Newton's homework one day in the park, even though they're centuries apart, but so go with the anecdote joke. When we studied Newton's law, we said F is equal to the gravitational constant times mass of 1 times mass of 2 divided by r squared, the distance between them. And we're like, oh my God, a conspiracy theory! It's exactly the same! Nobody panic, nobody, stress out too much. The idea behind this is that an inverse square law, which is when you have 2 particles, 2 objects, 2 something, and you have a distance between them, inverse squared. This is quite a common physics equation. So nobody panic. It isn't some weird phenomena happening in the universe. This is a thing that happens quite often, and you'll see it in a lot of other fields and a lot of other niches in physics and science. The constant changes. It's not the gravitational constant. Instead, we have a Coulomb's constant, which is 1 over 4 pi epsilon naught. Epsilon naught is the description of the permittivity of free space, which is kind of like a description, a value given to space, vacuum, of how readily available a charged particle can pass through it. It's weird. I know, we won't get too much into it. But K has a value of 8.99 by 10 to the power of 9 Newton by meter squared divided by Coulomb squared. Q1 and Q2 represent one charged particle and another, and you divide it by r squared, the distance between the 2 charged particles. The biggest difference with this and Newton's gravitational law is the fact that, well, Newton's gravitational law is always attractive. 2 bodies, 2 masses, can only be attractive to each other. They cannot be repulsed by each other. However, in electromagnetism, we stated earlier that like charges repel, which means they push away from each other, or opposite charges attract. And so it can do both. It can push away particles or pull them in together. It can do both things. Now, we're dealing constantly with little tiny, minute, tiny, insignificant, tiny electrons and protons, things that we cannot see. And so sometimes we're like, oh yeah, the force between these 2 things are tiny though. This calculation is BS, it's almost negligible. There are actually like really, really cool calculations that you can do. They're quite large in size. So for example, in this mathematical problem, we have 1 gram of electrons, only 1 measly gram of electrons, and we shove them all in a box. Okay, they're tightly packed in a tightly little box. The mass of one single electron is 9.1 by 10 to the minus 31 kilograms. We can determine the exact amount of electrons that exist in this box by dividing 1 gram divided by how much 1 electron weighs, and we know that there's 1.1 by 10 to the power of 27 electrons. in this. That's a lot of electrons. But we also know the charge of each individual electron. So if we multiply those two numbers together, we know what the total charge of the box is. And the total charge of the boxes is minus 1.8 by 10 to the power of 8 coulombs. Fantastic, good stuff. Let's get another box, right? The exact same thing, 1 gram, bunch of electrons jam-packed in there. And we place these two boxes 1 meter apart, and we treat these two boxes as point masses. Don't ask me why we do this. We do this. It's easier. It's too hard otherwise. But we do this, and we place them 1 meter apart. The force, the repulsive force between them, if we sub in all our values that we just calculated, the force between them is 3 by 10 to the power of 26 newtons. If you're a person who's not very familiar with newtons or what this value kind of represents, it is 1,000,000 times larger than the force between the sun and the earth. This is a big chunky force. It's chunky. That still only counts as 1. Kyle, thanks so much for the follow.